Week 8, problem 11. Figure below shows a bar of mass 0.25 kilograms that can slide without friction on a pair of rails separated by a distance of 1.2 meters and located on an inclined plane that makes an angle of 30 degrees with respect to the ground. The resistance of the resistor is R, which is 3 ohms. A uniform magnetic field of magnitude 0.5 teslas is directed downward, perpendicular to the ground, over the entire region through which the bar moves. With what constant speed v does the bar slide along the rails? Okay, so this is the exact opposite of what we did on the last problem. So I'm going to start by drawing this guy a little bit differently. A little bit finer. There we go. And we'll do some blue. Alright, now I'll go click. So we have our... So we have 30 degrees, and we have a bar like this. It's going to be sliding down this direction. So first thing we want to do is we know that there's going to be a mass times gravity pulling this guy down. Mass times gravity. And we want to find out how much force that's going in that direction. That guy right there. So the way we're going to do this is, there was kind of a mnemonic that I used for physics 1. So sliding, force downward will be sliding, so we're going to use sine. You can do the geometry and decompose the vector. You don't have time for that. So I'm going to call this force x. So force x equals mg sine theta. So you know that whenever you have a situation and you have the angle down here, that the force going down this way is going to be mg sine theta. And one way to kind of operational check that, is if you have a theta equals 0, then you're going to have 0 force sliding down. Sine of 0 is 0. So this right down, mg sine theta. I like to just have that one memorized. Siding sine going down, and that way, wait a sec, click, bam, that's easier. Sliding down. That way, just have that memorized, have that one out of the way. Alright, so now we know the force that's pulling this guy down the rails. So as it's being pulled down, there's going to be sort of a terminal velocity that's going to be created, because there's going to be a electromagnetic counter electromagnetic force, maybe, created going back upwards. So we're going to have a Lenz's law issue going on here. So, because we have a magnetic field. So let's see here. So I'm going to start off by writing Lenz's law then. So we have epsilon equals negative d flux dt, which equals negative VA dt, which equals we probably already have memorized by now, but I'm terrible at memorizing anything in life, so I do it this way every time. dv dt times A plus dA dt times B. Okay? We know the magnetic field is going to be constant, so this guy's going to be 0. And we know that A is going to be width times length, so dA dt equals d width length dt, which equals dw dt L plus dL dt times W. Alright, and then L is the length of the rod, so that guy's going to be constant. So this guy's going to be 0. So that we're going to have dw dt times L, which equals velocity. I'm going to put a little vector up there, just so that I don't get confused with voltage. Alright, so this is going to equal negative, I'm going to do this LVB, because we have the acronym then, everybody loves velvet bunnies. I love velvet, I love bunnies, everybody loves velvet bunnies. ELVB. If you're confident in life, you can skip straight to that step. If you're not, that's okay. I'm not, so I always write it out. So that's going to be the induced current, or induced voltage, electromagnetic force, as it's sliding down. Okay? That seems reasonable. And now, let's see, what else should I look at? So here, this is going to be a dot product, so we're not going to be able to use the full B here. So we're going to have to take into account, I'm going to say the sine of theta. Now that's just a complete guess, but I'm pretty sure it's either going to be cosine or sine. So now I'm going to look at this guy and think, no, I think it's going to be cosine. Because dot products in life are cosines. Are they cosines? They're sines. Cross products are sines. The dot products are cosines. So the direction of this plane right here is this way. So the angle, draw this guy out, draw that guy out. This is the theta we're talking about. When that theta equals 0, then we get the maximum amount of effect from the magnetic field and the plane. So when we get maximum at 0, then that means we're going to want to use cosine. Yeah. But then how does this relate to that? Are these the same angle? Alright. So here, I'm just going to do guess and check here. So I'm going to redraw this. I'm going to look at this guy. So right up here, completely flat triangle. Magnetic field going down. So theta equals 0. Therefore, this will have the maximum effect of magnetic field because we're getting the maximum flux through the area of this plane. Granted, we're not going to have any force pushing it down the hill, but that's okay. So to get the maximum force, we want to have cosine of theta. So, and then if it was 90 degrees, straight up and down, we have something like this. Magnetic field this way, block falling this way, and this would be 90 degrees, and there'd be 0 flux. So this guy is actually supposed to be cosine, not sine. And the way I did that was just guess and check. Because even though I know that between B and A there's supposed to be a dot product, which is the cosine, I'm not necessarily sure where this angle right here, which is the perpendicular angle to the plane, to the surface, how that necessarily relates to this angle. I know they do relate, but I'm not sure how exactly. So that's why I think it's easier just to guess and check. And this is how I guess and check. I look at the extreme examples. One where it's 90, one where it's 0, and then I see which one makes sense. That's kind of a hand-wavy, it works kind of solution. But go through that logic for a little while and be like, yeah, okay, it kind of works. And once it feels right, that's the easiest way to do it. Because if you try and do it using geometry and figuring it all out, then there's so many steps, you're probably going to make a mistake, and it's not worth it. And this way, it's so much quicker, and you're probably more likely to get the right answer. So I'm going to say that this then, right here, is the final. So that's the final voltage. So now we're going to use our next equation. Fire incinerates little bunnies. F equals I incinerates cross B. Which is same as, because we know that force equals EQ plus QV cross B. Well, this is measured in meters per second, so if you take that per second and move it over to the Q, then you got a current. And if it's just meters, that's an L cross B. Bam. And then this guy's 0. And this is where our fire incinerates little bunnies equation comes from. So not magic, it's this equation right here, F equals EQ plus QV cross B, that we've used forever. By forever I mean for like a month. And we just reapplied it. So erase this guy, boom. So now we have our fire incinerates little bunnies equation. And that's what we're going to try and work with here. So we know what the force is going to be. The force, we already figured out was mg sine theta. Because that's the standard block force on a block sliding down a ramp. Okay? And what are we trying to find? Speed. We're trying to find the velocity. Okay? And now we need to convert this I current, V equals IR, Ohm's law. Therefore, current equals V over R. I always have a hard time remembering this. So usually the way it makes sense to me is I do like the whole hydraulic analogy. Well, current is the flow of water or electrons. And so how much flow you're going to have is going to be proportional to the pressure on each side, you know, the voltage, divided by the resistance to flow. So if you have a whole bunch of like filters and labyrinthy type pipes, then it's going to offer a lot of resistance and you're going to have less flow. But if you have a lot of pressure on both sides, then you're going to get more flow. So this equation right here is the one that makes sense to me. So I'm like, okay, that makes sense. All right, so I'm going to rewrite this then again. Equals E over R L cross B. All right, now let's see if L and B are perpendicular. So cross product is sine. So L is going left and right, and B is going up and down. So yes, these two are perpendicular to each other. Might not look like it from this photo. Nope, that was terrible. From this picture, but that is 90 degrees. Is it 90 degrees? Yeah, I think it's 90 degrees. I'm going to say it's 90 degrees. Pretty sure it's 90 degrees. It's 90 degrees. So the direction of current. Now, when you're talking about up this way and down that way, then that's not going to be true. But on these portions right here, then that's going to be true. Those will be 90 degrees. So this is going to be E over R L B. And I say E, but I should really mean epsilon or electromotive force. All right, let's see. Now we know what electromotive force is. So we're going to have LVB times cosine of theta over R times L times B. Rewrite that guy one more time. Maybe zoom in a little bit so my handwriting will be nicer. We'll have L squared B squared V times cosine of theta over resistance equals, and what is it, mg sine theta? Mg sine theta. Alright. So now it's asking us for the velocity, because we know the length of the rod, we know the magnetic field, we know the thetas, we know the mass, we know gravity, and we know what resistance is. So we know everything here except for voltage. So I'm just going to solve this guy for voltage. So I'm going to do a little arrow, so I'm like, it's related, but I'm not actually saying how. So mg over L squared B squared times R times cosine of theta over sine of theta. Sine of theta over cosine of theta. There we go. Let's see. Mg sine theta, R goes up to the top, L squared B squared goes to the bottom. Yep, I'm going to say that's good. That all equals V, the velocity, which we're looking for. And there's a negative sign in there, but I don't really care. Alright, that's tangent, right? I'm going to make sure. Tangent. Say something here that says sine over cosine. Ah, you're killing me. Hop, hop, hop. Oh, why are there so many things that have SIN in them? Why is sin so prevalent? Wow, I was really thinking this would be easier. And I'm just going to assume it's sine over cosine. I'm mostly 100%, you know, give or take a bit. tangent equals sine over cosine. Bam. Thank you, Google. Giving me exactly what I want. Alright. Maybe put this pink, magenta, whatever that is. mg r over lb squared times tangent of theta. Alright. That will be easier when I wolfram it. And there's asking us for velocity? Yep. Okay. Okay. Now normally this is when I look at it, I'm like, well, that seems to make sense. It's like, yeah, I guess so. There's a lot of numbers in there. Maybe. Alright. So, mass is 0.25. 0.25. So I'm going to do it this way. 0.25 times gravity, 9.81. 9.81. Radius, or better phrased, resistance, 3 times tangent of 30, pretty sure it's 30. 30 degrees. Divided by quantity, L squared B squared, 1.2 squared times, then we had, how many tests? 0.5? 0.5 times 0.5 squared, which is going to be 0.25. Let's go with that. Wolfram, go. So we got 0.25, 3, tangent of 30, 11.8. That seems reasonable. What constant speed is it? Well, that is an answer. I'd go with that. Okay, I'm gonna be confident. Heck with this panzing around. Bam, 11.8 meters per second. Got it. $11.8. So, looking back, I really didn't know where I was going with this one, but you know that you're going to have a magnetic field and a changing area or magnetic field. One of the two. So you're basically going to have a changing flux. And if you have a magnetic field and a changing flux, then you're going to use Lenz's law. So you write up Lenz's law. Bam, right here. Then you write it out. You figure out what exactly is changing, and you get a final equation. This equation, it comes up a lot. That's why we have a mnemonic for it. Everybody loves velvet bunnies. But you know that they're not perpendicular to each other, so you're going to have to use a cosine-sine relationship. And the way I figured that out is guess and check. Like, cosine or sine. And then you use an example of, well, if this was, you know, this hill was straight up and down, or if this hill was completely flat, which one would make sense? Would you have maximum flux, minimum flux, and you reason it out. It's just the easiest way to do it. And if you do it a couple times, basically this is the only real kind of example you're going to get. Like, they're going to be similar to this. So if you understand this problem really well, you'll be able to do this problem every time. So after that, you get a relationship between the voltage produced and the speed, length, change of magnetic field, etc., etc. All right, you then use that to find the current, which we did somewhere around here, right down here. Current equals voltage divided by resistance, Ohm's law. All right, you then use that with your equation that we used earlier, that we've been using the whole time. Force equals electric field times charge plus charge V cross B. Well, the variation of we're going to use this is going to be fire incinerates little bunnies. It's the same equation, this is just written slightly differently. So, I guess I probably should have magnitude on that. It doesn't matter. So you use that equation, you plug in all the data you know. You know that the force pushing down on the block is going to be mg sine theta, which makes sense since sine is going to be greatest when you're at 90 degrees. and the block is going to have the most force pulling it down when it's, you know, literally just falling down. So we have mg sine theta. You put in everything. You look at for what you don't know, which is that guy right there. You then solve for him, and that's the answer you get. Yep, you go with that and you move on to the next problem. All right, they didn't ask us to find which direction things go, which is probably good. All right, sounds good. See you on problem 12.